Imagine yourself stepping into a room where time is softened and enlarged. A place where each second stretches out like a long, slow breath. Where the air itself seems to hold on to the moment just a little longer before letting it slip away. You probably would not last a full day among atomic clocks, not because anything is harsh or loud, but because the pace here is so gentle, so deliberate, that the mind begins to swim in the slow current of precision. And 1 second feels like a calm eternity. Welcome and settle in. If you enjoy drifting off to quiet science, please tap like and subscribe. And if you want to keep learning while you rest, there is a playlist link in the description to keep you company as you doze. How sleepy are you? On a scale of 1 to all, you find yourself at the threshold of a laboratory where time is not only measured, it is cared for. The door is soft on its hinges, and beyond it, the air is cool and dry with the faintest scent of clean metal and paper. There is a subtle hum coming from the vacuum pumps, a steady breath of machines that is neither urgent nor insistent, just present. The lights are gentle, more like a steady afternoon than a bright noon, and everywhere there are calm surfaces. Smooth benches, matte instruments, soft cables looping from one cocoon of metal to another. Nothing here ticks in the way you might expect. There is no clatter of gears, no brass pendulum swinging through space. Here, time is caught and cradled in the soft oscillation of atoms, in whispers of microwaves and light, in transitions so steady they can be trusted with the heartbeat of civilization. Imagine settling into a comfortable chair in a corner of this room, the fabric warm and supportive, and noticing that your own breathing slows in response to the unhurried pulse of the place. Somewhere inside a sealed vessel, cesium atoms drift through a quiet vacuum. They are coaxed and calmed with beams of light and carefully tuned fields. The second, the very second that your phone and your watch claim to count, is defined here as a certain number of gentle tremors in the heart of cesium-133, exactly 9,000 cycles of the transition between two hyperfine levels of its ground state. The numbers sound strong and bright, but in your ears they are just a soft count, a rhythm that goes on and on without fatigue, as if it were the breath of the planet in a small sheltered bottle. The walls, you notice, are thicker than usual, padded with quietness. The instruments rest on tables that float slightly, isolated from vibrations, as though they were on rafts on a still lake. The cables are tied neatly, the connectors polished to a delicate sheen. There is a comforting habit to it all, a domestic calmness that has evolved out of necessity. Heat must be steady here. Electric fields must not wander. Magnetic fields must be shielded and held in place, like a gentle hand steady in a cup of tea. A breeze would be a disturbance. A tiny imperfection in temperature would be a kind of weather that these clocks could feel. So the lab has learned to breathe evenly, to keep quiet in the way that libraries once did, to keep a stable, protective calm, so that atoms can sing their tiny song without strain. You may expect something grand, but the clock itself is modest, even humble in appearance. There is a cylinder of stainless steel, softly brushed. There are windows of glass and sapphire that reveal almost nothing to the naked eye. There is an array of lasers, their beams traveling silently through the air, as invisible conduits of persuasion. A whisper of red, a hint of green, a breath of near-infrared is scattered here and there, but to your eyes, the light is not a spectacle. Your senses are not overwhelmed, rather they are soothed. The numbers on small displays rise and fall, but not in a way that demands your attention. If you stare long enough, you begin to see the second stretch. You notice that the digits do not simply flip. They drift gracefully toward change, controlled by the most patient of metronomes. The patience is essential. The way a pendulum clock once relied on the steady swing of a weight, the atomic clock relies on the inner rhythm of the atom. Cesium has two nearly equal energy levels in its ground state, split by a tiny magnetic interaction. That splitting, that gentle difference, can be coaxed with a microwave field tuned precisely to the frequency that prompts the atoms to slip from one level to the other and back again. In an older style of clock, a beam of cesium atoms drifted through a cavity, a corridor where microwaves await them. The beam is filtered so that most atoms arrive in a particular state. They pass through, they feel the microwaves, and some of them change state. At the far end, a detector counts how many have changed. The microwave frequency is tuned to maximize this gentle flipping, and then held there like a violin tuned so carefully that it hardly needs to be tuned again. The second is measured by counting the microwaves as they oscillate in perfect sympathy with the atoms. Over time, clockmakers have learned to quiet the atoms themselves, to let them move more slowly, to free them from jostle and temperature. In the corner of the lab, you can imagine a small fountain, not of water, but of atoms. Laser beams, carefully arranged, meet in a tiny cloud. The atoms are cooled close to absolute stillness, their motion slowed to a crawl, until they behave like a calm flock resting on a still morning. They are then tossed upward in a gentle arc by additional laser pulses, rising and falling like soft seeds in a breeze, reaching the top of their flight where time seems almost to pause for them, and then drifting back down. On the way up and on the way down, they encounter microwaves twice, which enhances the sharpness of their response, like two quiet taps on a wine glass make the ringing clearer. This is a fountain clock, and its slow rhythm matches the mood of the room, where even the atoms are allowed to float in a long and patient trajectory. You look around and notice the materials chosen to steward this patience. The chambers are under vacuum so that nothing rubs or collides without necessity. The windows are transparent, but what they reveal is mostly emptiness, which is not a void as much as an invitation to stability. Softly glowing panels indicate the temperature. It hardly changes, and when it does so politely by fractions of a degree and then settles again. The lab hears its own heartbeat and calms it. The vibration-isolated table feels like a raft, yes, and the laundry of noise has been hung out to dry outside the walls. You can almost hear yourself thinking, and your thoughts slow down to match the room, your awareness of each second stretching. If you listen gently to the hum, you begin to perceive layers. There is the low breath of pumps. There is the higher, finer tone of electronics. There is the steady tick of code inside computers that do not tick in any audible way, but you feel them in the way the indicator lights pulse like fireflies in a meadow. The software learns the pattern of the atoms and keeps the microwaves in tune with that pattern. It is a conversation that never raises its voice. If the frequency is a little too high, the atoms indicate so, and the loop pulls it back. If it is a little too low, the atoms respond, and the loop gently nudges it up. This is feedback, not in the sense of a scolding, but in the sense of a teacher who listens and asks the next question that brings the student forward by a fraction again and again until the class and the teacher breathe in the same rhythm. There is a kind of subdued poetry here. The unit we call the second is not a guess, not a compromise between rough measurements. It is defined so that the cesium transition is the same everywhere and every time, in a way that is both universal and intimate. Anywhere in the world, on a mountaintop or in a basement, in summer or in winter, in a lab that is fancy or one that is simple, this frequency cuts through the details. It is one of the gentle anchors of the world. Decades ago, people tried to define the second by the rotation of Earth, by the swing of the planet's own pendulum. But Earth is restless, a little faster today, a little slower tomorrow, rocking, wobbling, drifting. The atom has less mood. It is steadier. And so the definition came to live with the atom where it could rest and be quiet. If you imagine walking softly to another bench, perhaps you sense a different flavor of calm. There is a trap of electric fields, a difference in detail but not in tone. Inside a single ion hovers, held by a gentle cage of force. It does not touch any wall. It is suspended as if in a thought, motion slowed by laser light that pushes and pulls in precise measures. Sometimes this ion is aluminum, sometimes it is ytterbium or mercury. The transition used here is not at microwave frequency, but at optical frequencies, far faster, far finer, so that the cycles are not in the billions per second, but in the quadrillions. The seconds feel even more spacious in such a room because the clock can count with incredible precision even within a tiny piece of a second, measuring the texture of time like fingers moving slowly over a smooth piece of fabric and noticing its faint weave. To work with such a high frequency, the lab has learned another soft trick, one that might make you smile in the way you do when you understand something fundamental and simple. It is the optical frequency comb, a kind of rainbow made of evenly spaced teeth of light generated by a laser that emits a gentle train of short pulses. Imagine the way a comb glides through hair, every tooth spaced the same. Imagine the light doing the same, a spectrum of lines as regular as a picket fence in the sun. This comb lets the lab compare a frequency in the visible or near visible range to something that can be counted with familiar electronics. The comb is locked on one side to the optical clock's light, on the other side to a microwave reference, and then the bridge is crossed in both directions easily. The device itself is quiet, a small box, a small hum, a soft glow, and yet it allows the lab to measure something that would otherwise be out of reach. The floors are solid and still. Your thoughts drift to how precise this all has become, and how calm it is to know that such steadiness exists. In the world beyond these walls, smartphones check time against global networks. Financial systems rely on it. Satellites depend on it. But inside this room, it is not about usage. It is about care. The lab understands that the clock needs to be freed from the push and pull of small errors. Blackbody radiation from the lab's warmth can shift the energy levels. Stray electric fields can tug at the atom's energy. Magnetic fields can move the frequency slightly. Each of these is measured, corrected, accounted for. The lab becomes a landscape without sharp corners, a field of gentle slopes, so that the atom can rest exactly where it should. The staff who tend to these systems move with quiet hands, the way one might adjust the focus of an old camera. Small turns, patient gazes, waiting for the blur to smooth out. Even the tables the instruments rest upon tell a story of patience. Granite or composite slabs, heavy and serene, rest on air springs or other isolators, so that the murmurs of footsteps do not ruffle the clock's attention. The ceilings have ducts that deliver air in a lazy stream, with filters that not only clean but also slow the flow. The walls carry copper meshes inside them to hush the restless buzz of radio waves that wander from cellular towers and monitors. The door has a subtle weight to it, helping to keep out drafts. The place feels like a library of time, a quiet archive where a uniform second sits on every shelf, ready to be lent to any device or network that needs it. Imagine yourself noticing how your own sense of time starts to slip and sway. The clock counts in a hurry, billions of cycles per second, yet the second grows longer for you. This place does that. When every little fluctuation is noticed, you begin to sense that time itself is not a collection of flashes, but a soft continuum you can float on. It is like listening to a musician who takes a piece at a very slow tempo, with each note clear, each beat distinct, and in the spacing between them, you find room for your thoughts to rest. You could sit here for an hour and feel as though you had experienced a day, but in a good way, a stretched way, like a quiet afternoon in a garden where the shadows move so slowly that you forget they are moving at all. Your imagination wanders to the way the lab feeds its carefully counted seconds into the world. There is not just one clock. There are many, forming an ensemble of gentle voices. They take turns singing the chorus of the second, and when one has a cough, the others sing a little louder while it recovers. The time scale known as International Atomic Time is a sum of these careful instruments, averaged and adjusted. Coordinated universal time sits nearby, staying almost in step with the Earth by adding the occasional leap second when the planet's rotation drifts. The network that distributes this time to the world uses radio signals, fiber optic links, satellites in orbit, each pathway adjusted for delays so that the time that arrives is not too early, not too late, but rested and accurate. In the lab, the delays are measured repeatedly, gently, and updated as if tucking the edges of a blanket so it fits just right. If you walk from bench to bench, you begin to absorb the rituals of maintenance. Some clocks are checked every day, some every week. Temperature sensors collect their letters and write a novel of values in a soft, scrolling a few characters per minute. Magnetic shields are inspected, their seams closed carefully as if they were a box holding a delicate scent. Lasers are tuned by turning smooth knobs with fingertips rather than fists. Data is reviewed, not hurriedly, but with the attentive eyes of someone reading a favorite book again, noticing details that others might miss. The people in this space have voices that fit the room, soft enough to keep the balance, clear enough to be heard by those who need to hear, unhurried enough to allow the finest adjustment. The gentle rhythm continues, and as it does, your mind softens at the edges. Imagine yourself simply watching, not needing to participate, finding comfort in the attentive care. You might think of how these clocks sense the shape of space-time itself. According to relativity, a clock higher up, farther from the center of Earth, runs a little faster than one lower down. The difference is tiny, but here, tiny is enough to be felt. These clocks are sensitive to changes corresponding to height differences of mere centimeters. If you raise an optical clock by the thickness of a book, it notices the change in gravity, a subtle lightening, and it quickened just a little. The lab could map the gentle slopes of the Earth's gravitational potential by moving clocks around, a kind of quiet geodesy conducted not with surveying tools, but with patient comparisons of frequency. The idea is simple and grand. Time runs a little faster atop a hill than it does at the bottom of a valley. The lab can measure this with the calm precision of an old tailor measuring a suit. The calm extends into the networks that link one lab to another. There are fiber optic cables that carry light pulses over hundreds of kilometers, connecting clocks in different cities, even different countries. The pulses are carefully timed and then returned, and the round trip is used to correct for delays, for temperature changes in the fiber, or any jostling along the way. The result is a time transfer that is as calm as the original clock. Imagine stretching a silken thread of light between one room and another far away, a strand so smooth that the slightest twist is felt and gently untwisted. There are also satellites that join the chorus, relaying the seconds with grace. The synchronization of the world becomes a quiet dance, with the lead taken by the atoms and the steps learned by the network, time shared without anyone needing to raise a voice. There is, in another corner, an optical lattice clock. Rather than a single ion, it uses a whole cloud of neutral atoms held gently in place by light that forms a standing wave, a pattern like calm ripples on a pond that never move. The atoms sit at the nodes or antinodes of this optical lattice, and the frequency of the lattice light is chosen carefully so that it does not disturb the atom's clock transition. This is called the magic wavelength, a phrase that feels poetic, but here is practical, a special point where two subtle shifts cancel and the atoms feel safe, as if the lattice were a hammock that supports them without pressing. The atoms are probed by a clock laser, its light like a caress that does not disturb the state more than necessary, and the readout is a gentle count of how many atoms sang in sympathy. The precision improves with the square root of the number of atoms, so using many atoms lets the lab hear the clock voice more clearly, as if a single violin were joined by an entire section, still playing softly. To build such clarity, the lasers themselves must be tranquil. The clock laser sits on a very quiet, very stable block, often made of a special glass or crystal that hardly changes its length with temperature. The laser is locked to this reference, and the line width becomes very narrow, like a thread drawn tight but not strained. The lab monitors the drift of this reference and corrects for it, patching any slow changes with a gentle push, just as one might shade a painting to even the tone. This hierarchy of quiet reminds you that peace can be built from the bottom up. If the laser is calm, the probe is calm. If the probe is calm, the atoms are calm. If the atoms are calm, the clock is calm. The gentle rhythm continues through these layers, until the counting of seconds feels more like listening to rain on a roof than like the clicking of a stopwatch. In the very earliest days of atomic clocks, the devices were larger and less refined. Yet even then, the desire was the same: to let the atom tell us in its own unflustered cadence what a second should be. Over the decades, improvements have come not through sudden drama, but through steady attention. Better vacuum, better shielding, better electronics, better understanding of systematic shifts. It is a progression that mirrors the way a skilled gardener improves a garden, not by tearing it up loudly, but by noticing where the light falls and where the wind tends to linger, then planting accordingly. The clocks have gotten quieter, not louder, and their song has gotten clearer. The perception that a second stretches to eternity in such rooms hints at something human. When a space is devoted to patience, we begin to feel the elastic qualities of our own attention. Your breathing slows. The sides of your mind that are used to rushing soften. The impulse to check the time falls away, replaced by a trust that time is already being cared for. In a world where many things scream for attention, a place designed for subtlety has a gentle gravity. If you let yourself float on it, you can find rest. And the scientists and engineers who work here often speak softly about their work, because the subject itself invites a similar rhythm. A clock in an airplane runs differently than one in the basement. A clock on a mountain runs differently than one by the sea. These are not mysteries here. They are accepted, measured, and folded into the work as calmly as a knitter changes color in a scarf. If a device must be carried to a different floor, the shift in its frequency due to the change in gravitational potential is estimated and later measured, and nobody is alarmed. It is a gentle correction, a few parts in a very large number, and these parts are tracked with the same equanimity with which one might track the phases of the moon. The lab is a temple of small differences, and small differences gather to make a profound steadiness. You can imagine the clock's microwave synthesizer as a carefully built cascade of oscillators, from a quiet quartz crystal up through higher frequencies, each stage stabilized by the stage below, each contributing its own tiny noise that must be minimized and arranged so that the final sum is as smooth as silk. The electronics in their metal enclosures are warm to the touch, but not hot. Their heat managed so that expansion and contraction do not whisper into the signal. Power supplies are chosen not for drama, but for calm. The cables are not just connected. They are arranged to minimize loops that might invite unwanted fields. Each of these choices is a kindness to the clock, a way of letting it do its work without distraction. At times, the lab reaches for ways to push beyond the normal limits that come from measuring quantum objects. Individual atoms are like tiny coins that land heads or tails depending on the probe, and the random noise from this measurement can blur the result. So the lab explores ways to correlate the atoms, to create subtle connections or squeeze states that reduce the uncertainty, again, not by forcing, but by tuning, by finding a resonance with the way atoms behave together. Even this is quiet, carried out with careful control of light and fields, another expression of the principle that less agitation yields more certainty. Clocks sit at the heart of navigation. The satellites in the global positioning system carry atomic clocks, and the signals they send are time stamps. A receiver on the ground listens to several satellites at once and uses the time differences to calculate position. For this to work, those satellite clocks must be kept in step with ground-based references. The ground checks the sky, and the sky informs the ground in a loop that is slower than the clocks but steady. The corrections for relativity are built right into the satellite's systems, like soft cushions under a cherished chair, so that the seat remains level even as the floor moves a little. The elegance of the solution is that it blends engineering with physics, not to dramatize, but to smooth. Imagine the smell of the lab in the early morning when the lights are still dim and the hum is a little more alone. Someone arrives quietly, sets down a cup with a cardboard sleeve, and checks the displays, seeing that the night has been kind. The logs are intact. The servo loops stayed locked. The counters rolled on and on, capturing every fraction. There is satisfaction here that does not need announcement. The gentle rhythm continues as day builds. But unlike elsewhere, here the tone does not sharply change. The lab resists abrupt transitions, preferring clarity to speed, preferring routine to novelty. It is not that change is unwelcome. It is just that change is treated with respect, planned, measured, and introduced in a way that the clocks can absorb without losing their composure. In the realm of optical ions, you picture a tiny spot of light resting on a single trapped atom, a glow so small that if you blink, you might miss it. The laser cools the motion of the ion by using the Doppler effect, catching it as it moves and easing it back. Then, through more delicate steps, cooling it further by addressing specific motional sidebands. The trap frequencies are tuned. The stray fields are compensated by adjusting voltages until the ion sits still in the trap center, motion steady and small. The object is to reach a kind of quiet where the ion nearly stops, at least in the noisy language of the world outside. Then the clock transition, a narrow line in the spectrum, is addressed with a probe that respects its fineness. A spectrum is recorded not in a rush, but over many repeats, averaging out random jitters to reveal a consistent peak that becomes the reference. If you think about the second being defined by cesium, you understand that optical clocks are not yet the official timekeepers for the definition, even though they surpass cesium in precision. That, too, is a process handled patiently by committees and intercomparisons, by technology that must be made robust and portable, by evaluating systematic uncertainties in labs around the world. The fact that the optical clocks are better is not a disruption here. It is a gentle change that will be adopted when the foundation feels ready, when the uncertainties are well understood, when the devices are mature enough to leave their rooms with grace. In the meantime, cesium holds the definition, and optical clocks demonstrate what can come next, both humming together in the same choir. Decades of development have brought us from the first resonant beams to fountains and lattices, from bulky components to quiet modules, from counting in megahertz to counting in petahertz. But your body, seated in that comfortable chair, sees only the slow expansion of the second. The longer you stay, the more the layer of precision translates into a cushion for your thoughts. Imagine resting your head lightly against the back of the chair. Imagine letting your hands relax in your lap. The gentle hum of the room has a way of smoothing out the sharp edges of your awareness. In this room, 1 second is both simple and spacious. The lab has learned to tame not only the things that push on the atoms, but also the things that tug at the electronics. Temperature drifts can be wrapped with insulation and control loops. Humidity is kept in a comfortable range. Even the flow of people is considered, because the warmth and movement of a person can be detected by the most sensitive instruments if they come too close. The rules are simple, and they exist not to forbid, but to create a shared understanding. Move quietly, keep the doors closed, give the instruments their space, check the logs, respect the stillness. In a way, the lab is like a small monastery dedicated to the worship of a calm second. The rituals, not religious, but practical, carried out with devotion. The effect of these clocks on the wider world feels expansive and seen. Electric grids become more reliable when their frequency is tracked against a stable reference. Communication networks slip bits through the air in perfect synchronization, making room for more conversations without overlap. Radio telescopes at far ends of continents combine their observations as though they shared a single giant dish. Their data aligned with nanosecond precision so that images of distant galaxies come into focus. Some applications need more than accuracy. They also need stability in the short term, which the optical clocks provide, so that in the moment when a measurement is made, the reference does not wag. Everything gains a little confidence from this steadiness, like a singer who finds pitch when the piano at her side is well tuned. The humble idea of counting cycles, tallying ups and downs, feels like the simplest of acts. The counters themselves are quiet instruments, small racks of devices programmed to count pulses cleanly, with input conditioning, with references, with careful attention to thresholds. Their displays show large numbers that roll smoothly, but you do not have to follow them. It is enough to know that with each breath you take, with each slow movement you make in the chair, the counters continue at an unchanging rate, like streams flowing under ice. In a subtle way, the clocks are also instruments for exploring whether nature's constants are truly constant. By comparing different types of clocks over time and over years, the lab watches for any trend that cannot be explained by known effects. If the electron to proton mass ratio were to drift, for example, certain transitions would drift more than others, and the pattern would emerge like a faint glimmer through fog. There are no alarms sounded here. The search is similar to listening for the quietest notes in a long symphony, a background that might have a slow wave in it. The lab conducts this listening with patience, letting the data accumulate, letting their uncertainties shrink comfortably. Your eyes follow a fiber that ducks into a small module where the optical frequency comb lives. It is a company of mirrors and a crystal, temperature controlled and quietly oscillating, its repetition rate stabilized, its offset frequency locked, forming the precise picket fence that spans the spectrum. Light from the clock enters and beats with the nearest comb tooth, and the electronic signal born of this beating is measured and compared. To the mind, these are abstractions. To the senses, they are just soft glows and low murmurs. The fact that all the complexity reduces to a gently humming box is somehow satisfying. like seeing a complicated story told with simple words. Every so often, someone gently dusts the optics. The air is filtered, but dust is part of any room, and on a long time scale, it settles. A canister of dry gas, a soft plume, a barely audible hiss. Lenses are cleaned with care, not scoured. The arcs of laser beams stay clean. Windows are wiped so that the view, faint though it is, remains clear. You begin to sense that maintenance here is not just a duty but a form of meditation, a way to align oneself with the instrument. While hands clean, minds rest. The gentle rhythm continues, and you can imagine hours passing with no loss of calm. The atomic fountain, when it launches its cloud, does so in a rhythm that repeats many times per second or per minute, depending on the design. The pattern is unhurried: preparation, launch, interrogation, detection, then again. Each step has been tuned so that the cloud neither sputters nor surges, but glides. The data recorded from each cycle adds a tiny thread to a long tapestry. At the end of the day, no single cycle matters by itself. It is the accumulation that produces certainty, a certainty that is more like a deepening quiet than a sudden revelation. When you glance toward the doorway, it frames the corridor that leads back to the outside world. Beyond the lab, people walk, cars pass, clouds move, and the ordinary clock on the wall ticks in larger jumps. Here, time feels like a surface you could run your hand across without encountering a scratch. You might think about time as it passes in a hospital waiting room, or in the last minutes of a concert, or in the moment before sleep. In this lab, it passes like a stream under a thick layer of leaves, silently, steadily, unfussily. It seems entirely plausible that a second could be stretched into a feeling that lasts for as long as you care to notice. If you had to spend a whole day here, you might find that your sense of urgency dissolves, and with it, the usual markers of time. You would drift in the measurement, and the measurement would drift in you, and perhaps that would be too much. You might not withstand a day, not because it is hard, but because it would gently peel away the impulses that usually keep you moving. In the corner, a small monitor shows a graph of frequency deviation, a calm wave that reduces as the averaging time increases. Ellen deviation tells its quiet story here. The longer you average, the smoother the frequency appears, and the curve falls as a simple slope on a log-log plot. You do not need to understand the details to feel the meaning. Waiting brings clarity. Patience makes the noise recede. The science of timing has adopted patience as a tool, not just a virtue, and it uses waiting as a way to let randomness cancel itself, the way long waves calm a lake. Beside the fountain, there is a black enclosure. Inside, the atoms are prepared with a magneto-optical trap, a configuration of laser beams and magnetic fields that brings the atoms to rest at microkelvin temperatures. The words are large, but the meaning is gentle. Cooler atoms move more slowly, and slower atoms are easier to watch without blurring. The trap is turned off, and the atoms float. A microwave cavity awaits. It looks like a simple can of metal, but inside, fields are tuned to uniformity, so that as atoms pass through, they experience the same fostering from beginning to end. The lab checks the fields by sending in reference signals, by measuring how the cavity responds, by controlling the shape of the field with tuning screws that move as quietly as thought. For optical lattice clocks, The preparation is equally measured. A pair of laser beams forms the lattice, their wavelengths chosen with care. The atoms are loaded into the potential wells of the lattice, in atom per site if possible, like beads placed on a string with meticulous fingers. Collisions between atoms can cause shifts, so occupancy and density are controlled. The probing is gentle and brief to avoid heating, but long enough to take advantage of the narrow line. The result is a spectrum with a crest as thin as a hair, and that crest serves as the reference, a place where the lab returns again and again with a steady hand. You hear, almost as a mirage, the thought that timekeeping used to be about the sky, about stars moving across meridians, about shadows shrinking and growing with the day, about sundials and mechanical escapements, and men in observatories marking the passage of stars. It is still about the sky in a way, but the sky has moved inside. The atoms are the stars now, and the transitions are the meridians, and the lab is the observatory. The tradition continues with new instruments, but the feeling of care remains the same. It is both technological and human, a bridge between the measurable and the lived. If you lean your attention into the soft sound of the pumps, you can almost mistake it for surf. It is regular, like a tide that neither rises nor falls too sharply. The vacuum they maintain softens the world for the atoms, removing air molecules that would jostle them, slow them, shift them. The pressure is measured not by looking at mercury in glass as once was common, but with delicate gauges that read the small presence of gas by the way it affects a hot wire or an ion current. These readouts sit in their corners like quiet guardians that report without drama. Values are logged again and again, making a story of stability. The painless truth is that almost nothing in this room moves quickly. The lasers do not sweep, they nudge. The tables do not shake, they drift. The atoms are not shoved, they are offered a path. And in this environment, time itself becomes a physical thing you can almost touch. Imagine holding a second in your cupped hands. In an ordinary day, it would slip through your fingers, thin as water. Here, it gathers like honey, clear and viscous. Viscous, and while it still flows, it flows with a leisurely texture that lets you follow its path. One of the clocks is connected to an outside link, an optical fiber that leads to another lab in another building. The two clocks compare their frequencies across this bridge, and the data flows in a slow stream. The difference between the two is so small that it might as well be zero for everyday life. Yet the lab can see it, can measure it, can say whether one is running a little faster or a little slower over minutes, hours, days. These comparisons keep each clock honest in the kindest of ways. They do not accuse, they simply provide companionship, a mutual reference. The clocks, in a sense, keep each other company, and the world benefits from their friendship. The gentle rhythm continues as you turn your mind to how these clocks participate in tests of physical theories. Symmetries are checked. Parity, time reversal, and other deep elements of the universe are explored through transitions that respond in particular ways to fields. If a new kind of field were to waft through Earth, like a breeze from an unknown realm, it might shift a clock in a particular pattern. Networks of clocks could watch for such patterns, and because they are so stable, they would be sensitive to even very faint effects. This is not sensational in the lab. It is simply another dimension of careful listening. The instruments are not only for keeping appointments, they are for speaking quietly with the structure of reality. If your eyelids feel heavier now, that is all right. The environment invites it. Imagine letting your gaze rest on a softly glowing display that shows frequency offset in parts per quadrillion. Numbers that change with the steadiness of clouds drifting. Your breathing slows further. The chair feels warmer. The hum becomes your lullaby. The second stretches again, and in its stretching, it does not crack. It simply becomes more spacious, like a corridor that opens into a hall. In such a space, it is easy to be content with small thoughts, with slow reflections, with gentle understanding. There is a comforting reliability to the knowledge that behind the ordinary objects in your life, from phones to power grids, from cameras to internet routers, someone is tending to time with this level of care. The world sometimes feels messy, but the seconds are not. They are kept in line by people and instruments that prefer calm to noise, clarity to chaos. It is not a glamorous task in the theatrical sense, but it has its own deep beauty, the beauty of consistency. When you think of a second as a container that must be made the same every time, you respect the effort that goes into building and polishing that container. On the optical bench, every mirror mount and lens holder is tightened just enough and no more. Screws are turned to feel, a feel that comes with practice, the feel of not squeezing the metal so hard that it warps, and not leaving it so loose that it drifts. The alignment is checked by watching the glow on a card, by seeing whether the dot sits where it should. The air is very still. The beam glides through the same holes in the same irises hour after hour. The lap is allergic to draft, and so the air handling is designed to avoid gusts, to spread flow over large areas so that no single stream disturbs the optical paths. In another rack, a disciplined arrangement of microwave synthesizers sits, with digital controls and small screens that display frequencies with many digits. The digits are not for show. They reflect the actual control of phase and frequency that these instruments can achieve. Their references come from a hydrogen maser, perhaps, a device that carries short-term stability with particular grace, or from the cesium clock itself for long-term stability. The blend of references is a craft. One gives quick calmness. The other gives enduring calmness. Together, they form a base that can be trusted during moments and during days. The history of timekeeping is a slow march through different physical phenomena. Pendulums were once the quiet heart of clocks. Their period depended on length and gravity. Balance wheels came next, with hairsprings and escapements that released energy in measured bites. Quartz resonators arrived, vibrating with electric neatness, insensitive to many disturbances and much more stable. The leap to atoms was a deepening of the concept, a step into the fundamental. Now optical transitions and their lasers are the new standard bearers for precision. Each transition has brought with it a new relationship to time, and each has had its version of this room, a space where the chosen oscillator is sheltered and attended to. You consider how your own experience of time changes with your state of mind, with your attention, with your feelings. In the lab, the second is something like a physical constant, defined and held in the clean grip of technology. In your life, the second expands and contracts based on experience. Both can be true at once. This is comforting. It means that while there is a hard, steady definition when needed, there is also room for your inner life to move softly within that guardrail. The lab provides the guardrail. You provide the weaving path within it. Imagine yourself feeling safe because the boundary is clear, and free because you do not need to attend to it. The world's official time is determined by comparing many clocks across continents, weighting their contributions, and producing a time scale that updates not in leaps, but in quiet increments. That time scale is then disseminated. Laboratories publish the differences between their clocks and the official time so that anyone can align to the common heartbeat. The process is administrative and technical, yet, in essence, it is a way of keeping everyone together. The little differences are reconciled, the big ones corrected, and the result is a gentle coherence. Networks profit, people profit. Devices cooperate. A calmer world emerges, at least in this one dimension. The gentle rhythm continues as you take another long, slow breath. You can imagine the lab at night now, with fewer people, lights dipped, and the instruments untroubled by footsteps. The clocks are not alone. They are part of a community of many labs all over the world, each preparing atoms in their own way, each counting cycles, each sending their results to a central place. The community is not competitive. It is collaborative, because it is hard to keep time alone. Spanning time and distance requires cooperation, and that cooperation is a quiet kind, a willingness to share data, to standardize procedures, to learn from one another without noise. The gentle arrangement of the room conceals a great deal of thought. Cables are separated by function so that noisy currents do not sit next to sensitive signals. Lights are chosen with spectra that will not disturb photodiodes. Materials are selected for low outgassing to keep the vacuum clean. Even the screws on the flanges are tightened in a pattern that does not warp the metal. None of these decisions is flashy. All of them add up. Together they create the cocoon. Inside it, the atom sings. Now, before you drift too deeply, here's a quiet invitation to leave a small trace of your presence. What time is it for you at this exact moment? And now, we continue. Your thoughts can float away. There is nothing to figure out, nothing to solve. The clocks do the work. You can simply sit with them and feel their pace. When the lab prepares a cesium fountain, the cycles of cooling and launching might be accompanied by small clicks as shutters open and close, but those clicks are more like soft switches than like the ticks of a clock. The microwaves in the cavity do not produce a sound you can hear. The detection light is too faint to be anything but a small spot on a sensor. The people who care for the fountain sometimes glance at a display that shows the transition probability over frequency, a smooth, symmetrical line with fringes. They adjust the center point, making sure the instrument sits right on the top. The shape of the line is beautiful in its own way, like the bell curve that appears in many places in nature and mathematics. Here, it is called a Ramsey fringe pattern, and it is both a picture and a tool. The microwave resonator is a piece of metal, precisely shaped so that the field's inset have a mode that matches the atom's needs. It could be a simple box, but it is made with care, polished in so that the fields are uniform, and tested with gauges that measure reflectivity and phase. These are not household terms, but they describe straightforward qualities. How much of the microwave gets in, how it advances through the cavity, how much comes back out. The relationship between the field and the atoms is tuned so that the atoms feel exactly the right persuasion, not too strong, not too weak, so that the transition is driven without pushing beyond what is clean and reversible. In the optical ion trap, electrodes create a quadrupole field that holds a positively charged atom in place. Voltages are applied and adjusted. Stray fields are compensated so that the trap center is centered where the fields are symmetrical. The ion's motion is cooled by lasers tuned just below a strong transition, so that when the ion moves toward the laser, it sees the light as slightly bluer and absorbs it, receiving a gentle push that slows it. Then, with more refined steps, sideband cooling removes energy from the specific vibrations of the ion in the trap until it is near its lowest possible motion. The process has been refined to the level of everyday routine in the lab. It is as complex as learning to play an instrument well, and as soft as practice feels when the music becomes familiar. You might smile at the idea that clocks can be affected by temperature, not because of random fluctuations, but because warm environments create a sea of light, black-body radiation that slightly shifts energy levels. The lab measures the temperature of the clock's environment because even a small change can matter at the level of parts in 10 order 10 tit. Thermometers, simple and quiet, are placed at strategic points, and their readings are combined into a model that predicts the shift. A correction is applied as calmly as a tailor adds a small seam allowance. Other shifts are considered too, the quadratic Zeeman shift from magnetic fields squared, the Stark shift from electric fields, the collisional shift from atoms interacting with one another. Each has its character, each is domesticated by measurement and correction. The very idea of a second has threaded itself through cultures in many ways. Ancient people divided the hour into smaller parts, but their seconds were not fixed. Mechanical clocks began the long process of standardization. Atomic clocks closed it. The second now is a thing that can be carried from place to place, transferred without losing form. It is not heavy, but it is full. It is a vessel that holds many cycles of a natural oscillation chosen for its constancy. You carry such a vessel in your pocket every day, not the atom itself, but a borrowed stream of seconds from the global standard. It means something quietly amazing, that everyone on Earth can agree on a moment, that simultaneity can be established across continents with only tiny disagreements. It is the kind of achievement that makes the world feel smaller and safer. In the lab, when a new system is being built, there are times of patient troubleshooting. A signal is missing, a line is too wide, a temperature refuses to settle. The team works through it calmly, checking connections, verifying code, looking for a cable swapped or a mirror misaligned. The solutions, when they come, are rarely dramatic. They are a twist of a knob, a resoldered joint, a modified parameter. The way the team approaches such tasks mirrors the way the clock approaches time, in small steps, gently corrected. The habit of mind that grows in such a place can be carried into life outside. Preference for clarity, for steady improvement, for rest between changes. Your mind, bathing in this unhurried narrative, may drift to whatever slows you in your own life. A window with a tree outside, a kettle that takes its time, a book you read softly. The lab has that quality. It is a human construct designed to be a sanctuary of steadiness. Imagining yourself there is another way of inviting that steadiness into your evening. Imagine your breath as a clock, not a harsh one, but a tender one. Inhale gently, a small rise. Exhale, a small fall. The rhythm does not need to be perfect. It needs to be kind. With each breath, another second slips by. You, and you have no need to chase it. It will come to you. Time transfer is an art all its own. Two-way satellite, time and frequency transfer, fiber links with active stabilization, common view measurements of signals that both ends can see. These methods maintain the coherence of timing across distance. Small delays are accounted for. Velocity and gravity are accounted for. Equipment drift is accounted for. Residuals are written down and watched for patterns. The instrumentation has matured so far that the limiting factors are no longer obvious. Sometimes they are in the environment, sometimes in the understanding of the equipment, sometimes in the regularity of the path. The people who do this work are patient by nature, perhaps because they have trained themselves to think in averages and long time scales. You can almost hear the tick of world time as a soft metronome somewhere beyond the walls, not because it is actually ticking, but because the knowledge that it is being maintained gives a sense of backbeat. In the lab, nothing is compelled to match that tick. Instead, the lab serves the world by being more precise than needed and transferring its precision outward. It is the armchair on which the world's time rests for a moment before returning to all the scattered clocks that display it. Clocks have their quoted uncertainties, careful budgets compiled from contributions, environmental effects, measurement noise, electronics. These budgets are not disappointing lists. They are recipes for serenity. They say that a little of this matters, a little of that matters, and together they compose a small uncertainty that can be lived with. Over time, these budgets shrink as new techniques are found, and the lab celebrates quietly, with coffee and perhaps a hand placed gently on the instrument's side. The sense of accomplishment is calm rather than jubilant. It has the feel of a gardener seeing a plant flower for the first time and simply standing in the doorway to look at it for a moment. The world outside sometimes imagines laboratories as cold and impersonal. In this one, you can sense warmth, not in temperature but in temperament. There is care in the arrangement of things, care in the scheduling of tasks, care in the way that data is recorded and archived. The instruments themselves become familiar. People give them names, might speak to them in quiet citas, might chuckle when a subsystem is being particularly fussy. The machines are not alive, but the relationships to them are human, and that humanity is another layer of gentleness in the space. You are drifting, perhaps now. Your attention slides across the tops of words. The phrase optical lattice comes and goes. The phrase frequency comb appears like a ripple and fades. The phrase hyperfine transition leaves a faint ring in your mind. You need not hold them. They weave a blanket of technical softness that you can pull around your shoulders as you breathe and settle. Imagine yourself lying back, eyes half closed, listening to time being counted not as a demand, but as a comfort. At some point, the lab will turn a page in the book of time and embrace an official redefinition of the second to be based on an optical transition. That day will be noted in publications, marked in records, and the change will be quiet. The old definition will be honored for how well it served. The new one will be welcomed for how much more precisely it can serve. The lab's routines will adjust in small ways, new instruments will carry the standard, and the world will continue untroubled. You will not notice on your wristwatch. The internet will not hiccup. The clock in your kitchen will not blink. But somewhere, in rooms like this one, the letter of the definition will have shifted to match the increasingly gentle song the lab has been keeping for years. Each second that passes here is not just counted, it is shaped by the care around it. That is why it can feel so long. The attention paid to it stretches it. Your attention, too, if you choose to give it, will stretch it. If you let the next breath be a second, you can feel the elasticity yourself. Inhale. 1. Feel 1. The second rises and falls in you and in the atom, and the two are not at odds. They are different voices in the same choir. One biological, one physical, sharing a common gentle beat. The gentle rhythm continues as you imagine the small differences between labs in different climates. One lab might hear a bit more hum from trains, so it compensates. Another might be in a building that sways slightly in wind, so it pays attention to mounting hardware. Another might face larger temperature swings and learn to keep the interior very stable. All labs adapt. The variation becomes a source of resilience. By sharing approaches, by comparing results, the community learns, and the clocks become better everywhere. The patience of counting is mirrored by the patience of listening. To stabilize a laser to a cavity, one technique is to apply a small modulation and listen to how the light reflected from the cavity changes. From this, a signal can be derived that tells whether the laser is above or below resonance, and feedback is used to correct it. This is optical feedback, and it is the epitome of a quiet conversation between a device and a reference. The method is robust and kind of way of making many small corrections instead of one big one, letting the system stay centered like a person practicing balance on a beam with microscopic adjustments of foot and ankle. The room offers no surprises. You can rest assured that if a surprise occurs, it will be handled. The systems are designed with margins. If a laser unlocks, a routine tries to relock it. If vacuum pressure rises, an alert appears quietly and someone comes, calmly, to address it. There is readiness here, but not tension. Preparation takes away fear. Knowing that someone is watching, even if the watching is through software, creates a sense of safety. Around the lab, photographs and notes mark milestones. The first day the fountain reached a certain uncertainty. The first time the ion trap ran through a night without a glitch. The first link established to another lab over fiber. These are mementos, light touches, like postcards on a refrigerator. They bring a gentle pride into the room, the feeling that the work is not just work, but craft. and that craft has a history. The second has a texture here. That texture is smooth, with a hint of fine grain that you only feel if you drag your finger across it slowly. To feel it, you must slow down. In ordinary life, you do not slow down enough to feel it. Here you do. Sensitivity increases with rest. The lab offers restfulness as a method. You can borrow that method for yourself. Imagine letting your attention settle on one small sensation. Perhaps the weight of your body on the chair, or the feeling of the fabric against your skin, or the coolness of the air along your cheek. Stay there for 2 seconds, then 3, then 4. Time extends. The second becomes large and gentle, like a pillow you can shape just so. At the edges of the lab's instruments, where cables meet, where beams are aligned, where screws are tightened, there is a culture of note-taking. Notebooks, digital and paper, are kept tidy. Entries are dated, diagrams are sketched. Everything is recorded with enough detail that someone else, or the same person a month later, can follow. This habit is not just practical, it is also another path to calm. When the world is documented, it becomes less mysterious. The mind is set free to rest when there is a record to return to. The tolerance for imperfection in such a lab is carefully chosen. Not everything must be perfect. Some roughness can be allowed if it does not propagate into the clock's operation. This selectivity is a kind of wisdom. It means that effort is spent where it matters and not wasted where it does not. The overall impression this creates is one of lightness. The work is serious, but it is not heavy. It is focused, but it is not tense. It proceeds with the ease that comes from knowing where to push and where to let go. There is also room here for wonder, subdued and continuous. Imagine the electricity that animates the laser. Imagine the structure of the atom. It shells and spins. Imagine the quantum states that are probed, superpositions that exist for a while and then collapse when measured, all guided by the soft pressure of photons. Imagine the field shaping space invisibly. Imagine the plays of frequency and phase. None of this needs to become mathematics in your mind right now. It can remain as a set of images, a tapestry of invisible waves weaving through a quiet room and you resting in a chair. As the tapestry continues to weave, we can think of time as a river, yes, but in the lab it is more like a small lake with a smooth surface. The splashes of stones are not needed. The waves that form are tiny and quickly damped. A friend might sit with you on the shore and not speak for long minutes, both watching the same water. That is what it feels like to be among atomic clocks. The companionship is in the shared attention, not in speaking. There is a sincerity here that asks for nothing and gives steadiness. In a future not far off, clocks might become even more portable, their precision packaged into units that can be carried to mountaintops and deep valleys, used to sense the gravity field in regional detail, to monitor aquifers, to watch for changes in mass distribution. The idea is practical and tender. It means that the timekeeper will not be locked in a room forever. It will walk among us, still calibrated, still calm, but independent enough to travel. Even then, central labs like this one will remain. They will be the hearths that maintain the flame the places to which all portable clocks return to be checked and polished. Take another slow breath. The second stretches. Your eyelids might flutter. It is all right to let them close. The narrative continues even if you do not catch every word. The room remains still, whether you notice it or not. That is the point of such a room and of such a minute. It is reliable even in your inattention. There is kindness in that reliability. It means you can rest. The instrument does not need your vigilance. It has its own. Somewhere, a small alarm light glows amber to indicate that an environmental threshold was crossed earlier and corrected automatically. A minor fluctuation of no consequence now. The log shows it. Someone will note it in the morning. The systems are resilient. The correction worked. Calm returns, and the gentle rhythm continues. The experience of such a place leaves you with the sense that even small disturbances can be handled if approached with the same patience that underlies the work. If you stay in the room long enough, the day will pass with very little change. The sound stays the same. The light changes only if someone dims it further, sensing that night has fallen. The display scrolls continue. The second continues. The staff may rotate, a few people leaving, a few arriving. Their presence is steady, their motions measured, their voices low. The continuity is uninterrupted by the handover. That, too, is part of the craft, to make transitions invisible to the instrument. Lying in your bed, you can imagine these rooms always running somewhere, perhaps in your own city, perhaps far away. That image can be a lullaby. The knowledge that a group of people is tending the second can be soothing in the way that the knowledge of a lighthouse can be soothing to sailors. It is a point of reference that does not succumb to weather. It is there, and you can rely on it even if you never visit. The lab is full of tiny, lovely constraints. The path length of a laser must not change by the thickness of a hair. The temperature of a cavity must not drift by the smallest fraction of a degree. The beam must not wander by the width of a speck of dust. These are the scales at which care operates here. To think of these scales is to feel a gentle awe, not for the difficulty, but for the intimacy with which the lab knows its own body. The instrument is a body with heartbeats and breath, and its caretakers are physicians of stillness. You would not withstand a day among these clocks if you needed action to stay awake. But if your need is rest, this is your room. The second expands to hold you. The oscillations smooth into a song that plays in the background of your thoughts. The data flows past like water in a canal, moving so slowly that you can count the leaves floating on it, one by one if you wish, or let them pass uncounted if you prefer. Both approaches are welcomed here. You can engage the mind with the detail or let the detail wash over you, while the deeper reassurance, that time is cared for, settles the deeper parts of you. There is an art to making the invisible visible. Here, that art is exercised by turning invisible cycles into counts, invisible shifts into corrections, invisible oscillations into readouts. The readouts are not thrilling, but they are satisfying. The graphs do not spike, they tend to flatten. The logs do not shout, they murmur. The results are not ephemeral. They become part of the permanent record, a contribution to a world that needs foundations. When the lab speaks to the public, it does so with photographs and analogies, often involving pendulums and metronomes, still or slow, and sometimes with the atom itself represented as a small sphere with shells outlined. Those images are helpful, but the true essence is in the feel of the place, which is why imagining it is so effective right now. Imagine the quiet hum. Imagine the soft light. Imagine the stillness of beams guided by mirrors. Imagine the vacuum that robs the air of its urge to jostle. Imagine the atoms floating slowly. Imagine the second expanding. The longer you rest here, the more clear it becomes that timekeeping is close to the heart of order. When things can be placed in sequence reliably, when processes can align, when effects can be timed, complexity becomes manageable. Time is the backbone of coordination. The lab, by tending to the second, tends to coordination. It is a hidden service of the world, and you can be grateful for it in a way that requires nothing of you but an exhale. Your eyelids may be fully closed now. If so, the words are simply a texture on which to dream. The clocks do not mind. They will continue to count whether you are listening or sleeping. Their patience is vast enough to include your rest and to accompany it. Imagine this patience as a blanket tucked around your shoulders. Imagine that the blanket is woven from light and fields, from hyperfine transitions and lattice wells, from feedback loops and stabilized platforms. It is a soft weave. It keeps out the noise. It lets in the breath. If some small part of your mind remains awake and wants a morsel of additional detail, you can feed it quietly. Cesium clocks often use Ramsey interrogation, where two pulses of microwave radiation, separated by a period of free evolution, interfere to produce a pattern from which the resonance can be determined with great accuracy. The details of pulse length and separation are tuned to the trade-offs of coherence time and signal strength. For optical clocks, the probe may be a Rabi or Ramsey sequence with extremely narrow line-width lasers, and the coherence time may be extended by avoiding perturbations and by choosing transitions that are less sensitive to fields. Frequency combs, mode-locked and stabilized, bridge the optical and microwave domains so that counting can proceed. Each of these techniques is like a careful finger on a string instrument, finding the harmonic and letting it ring. The clocks themselves are the heart of a broader ecosystem that includes calibration laboratories, standards organizations, and application developers. Each part depends on the other, and the interfaces are crafted to be robust and clear. Protocols are defined so that data can be shared without misunderstanding. Metadata is recorded so that values have context. These layers of clarity, all conceived and carried out with gentleness, create a networked calm that extends beyond the walls. If you were to tour 3 or 4 labs in a row, the differences would be interesting, but not jarring. One might prefer certain materials. Another might have a different arrangement of benches. One might use a particular method of optical stabilization. Another might have chosen a different approach. Yet all of them would share the same overall feel, the same preference for slow change, for thorough documentation, for tuned intervention. You would emerge from such a tour with the sense that the world has many rooms where time is kept with love. In the dimness, it becomes easy to imagine the clocks themselves as characters, not in the literal sense, but as presences. The cesium fountain has the feel of a calm elder, established and steady, while the optical lattice clock feels like a young virtuoso, precise and nimble. The ion trap is the soloist, alone but expressive. The hydrogen maser is the quiet companion, comforting in the near term. The frequency comb is the translator, eloquent and modest. Together, they form an ensemble that performs the same piece every day and in doing so keeps the world in tune. As sleep approaches, you may find that words like hyperfine, comb, lattice, cavity, trap, maser, Ramsey, and Allen drift like feathers, landing softly and then lifting off again. You do not need to hold them. The content they signal has already seeped in at the level it needs to. You understand in a resting way that there are rooms on Earth where people have built sanctuaries for seconds. In those rooms, a second is long enough to rest in. That is enough for tonight. The narration returns quietly to you now, to your room, to the present. You are safe. The night holds you. Somewhere, someone tends to the world's seconds, and they do so with the care and gentleness you have felt here. If your eyes are closed, let them remain closed. If your body is heavy, let it sink deeper into the bed or the chair. The second is expanding around you, not to push you, but to soften your thoughts, to give them room to settle. If you liked this gentle journey, you can subscribe and leave a like so we can keep releasing videos this often. And you can use the playlist link in the description to keep learning while you drift. Rest well, breathe softly, and let the calm count of the clocks carry you into sleep.